Hi, I'm Dan. This is Roei. We're going to be talking to you about local testing for multiplicity codes. This is joint work with Amnon Tashma. So, quick reminder about local testing. We're given a local error correcting code and a word, and we want to distinguish efficiently between the case where the word is in the code and the case where the word is far away from the code. So we query the word in q places and we return either yes or no. If the word is in the code, we want to always return yes. And if it's not in the code, we want to return no with probability that's at least proportional to the distance between the word and the code. One of the first examples where local testing was studied is Reed-Muller codes. These can be thought of as functions from FP to the M to FP. And we say a function is in the code if it coincides with the values of a low degree polynomial. Now, local testing for Reed-Muller codes was studied in the low degree regime as part of the PCP literature. And there's another line of works that studies it in the high degree or low characteristic case that we rely on in this work more closely. Now, all of these works analyze basically the same test, and they differ in their analyses. And this is the test where we restrict to a small dimensional affine space and check if the restriction is of low degree. We call this the dimension k test, which uses a uniform k-dimensional affine subspace. Now, any function on k variables is equivalent to 1 of degree at most p minus 1 times k. So the k-dimensional test is trivial if the degree is above this value, which is equivalent to saying that k is below some minimal dimension, which we call the Reed-Muller testing dimension, and is around d over p minus 1. The state of the art for analyzing this test tells us that as soon as the k-dimensional test is non-trivial, it's a good local tester with nearly optimal soundness, at least in the parameter regime we consider, which is close to the amount of queries times the distance. So we can look at this theorem of Kaufman and Mintzel from a few months ago, which says that the soundness of the k-dimensional test is optimal up to a loss which is polynomial in P. What are multiplicity codes? Multiplicity codes are a generalization of Reed-Muller codes, which contain not only the values of the polynomial, but also the value of its derivatives up to a certain order, where we have a bound on this order, which we call S. So we can think of them, again, as tables or functions from FP to the M to a larger alphabet, where each character of this alphabet contains many copies of FP, and we can think of these copies as indexed by weight less than S tuples, where these tuples correspond to the directions with respect to which we take the derivatives. So such a table is in the multiplicity code if there exists a polynomial, so that the table is equal to the values of the polynomial and its low order derivatives. Multiplicity codes have similar local correction algorithms to Reed-Muller codes with similar algorithms. To define the restriction correctly, we need to apply a chain rule map. This is because the size of the alphabet of the multiplicity code depends on the dimension we're in. So for example, if we look at the derivative of a polynomial restricted to a line, this is equal to a linear combination of its directional derivatives, where the coefficients of the combination are the direction of the line. So once we define everything properly, multiplicity codes are locally correctable with algorithms reminiscent of the Reed-Muller algorithms. And they were originally used to construct locally correctable codes with rate close to 1, and later used to construct locally correctable codes in the constant rate regime with small query complexity. A natural question brought up by Copperty in 2013 is, are multiplicity codes also locally testable? And do the algorithms for Reed-Muller codes work for multiplicity codes? So let's discuss this a little bit. Similar to the Reed-Muller case, any function in the multiplicity setting is equivalent to 1 of degree k, at most k times p minus 1 plus s minus 1 times p. So the test is only interesting if our degree is smaller than this value. If we think of k as small and s as order p, this bound is much larger than the Reed-Muller dimension, the Reed-Muller bound. So we can hope that the k-dimensional test is effective for much larger degrees than in the Reed-Muller case. So what we want to know is how good is the k-dimensional test for multiplicity codes. An interesting example to look at is the dimension 1 case, the line test, and hopefully it will be effective up to degree around s times p. Let's look at the polynomial x to the py minus y to the px. This polynomial, in terms of its values, is always 0, but its derivatives are non-zero. So it's a perfectly fine code word of the multiplicity code with 2 variables and of degree p plus 1. However, if we restrict this polynomial to any line, it drops a degree. This can be seen if we look at the coefficient of t to the p plus 1 as a polynomial in the coefficients of the line. This coefficient is a value that's always equal to 0. So this shows us a failure not only of local testing, but of what's known as local characterization. That is, not only is the proportion of lines that attest to the fact that this has degree p plus 1 small, in fact, all the lines are fooled by this polynomial. So the next, and this happens at a degree of p plus 1, which is much smaller than the degree bound we were hoping for of around s times p. So the next thing we can look at is planes. And that's actually what we show. We show that the plane test is a good local tester for multiplicity codes up to a degree bound which is close to the one we hoped for, up to a degree bound of p times s. Now, an important caveat here is that we show this only for s smaller than p. Given this, we show that the plane test is a good local tester where its soundness is around p to the minus order s. We believe the soundness could be improved, but maybe we can talk about that later. This result we get this result by using 2 main ingredients. The first is showing local characterization. That is, we show that if a polynomial is of degree larger than d, then there exists at least one plane that tells us that its degree is larger than d. The second part is showing that, well, we hoped earlier that the k-dimensional test would be effective for larger degrees than in the Reed-Muller case. We show that it's effective at least for the same degrees. So we show that if k is above the Reed-Muller testing dimension, then the k-dimensional test is also a good test for multiplicity codes. So while the first part tells us that there's at least one plane, the second part will help us show that the proportion of planes is non-negligible. So let's talk about how we do this. Given these 2 ingredients, suppose we have a table from fp to the m to our multiplicity code alphabet. Because of the Reed-Muller testing properties, if we pick an intermediate 10s dimensional subspace, a large proportion of these will tell us that the table does have a large degree. Within each one of these, there's at least one plane that tells us that the degree is above d. So the soundness for the plane test is at most the number of planes in 10s dimensional space times the soundness for the 10s dimensional test. And because there aren't too many planes in 10s dimensional space, we get our result. Okay, let's talk a bit about the proof technique. We'll start with the warm-up case. So let's look at the line test for Reed-Muller codes and show that it is a good local characterization when the degree is smaller than p minus 1. So we have this parameter d, and we have a polynomial of degree larger than d. We want to show that at least one line tells us that its degree is larger than d. We write this polynomial out as a combination of monomials, where this shorthand x to the I means a product x1 to the I1, x2 to the I2, etc. And we know that at least one monomial is of degree larger than d. So let's focus on one monomial. We'll call it IM with degree larger than d and remember it for later. And now we'll make a generic substitution. X equals at plus b, where a and b are parameters, they're vector parameters to be chosen later. We'll be interested in the coefficient to coefficient polynomial, telling us the coefficient of the monomial t to the d plus 1 as a polynomial in a and b. If we show that this polynomial is non-zero for some a and b, then we found an a and b which define a line, and the restriction to this line has degree larger than d. So let's write out the restriction as and simplify. It's a sum over all monomials, where for each one we sum over all the ways to split it into two parts, I1 and I2. We get a binomial coefficient, and the power of t will be the weight of I1, and we get a and b raised to the powers I1 and I2 respectively. So if we look again at our specific monomial and we split it into two parts, where the first part has weight d plus 1, this makes a contribution to the coefficient of t to the d plus 1. This contribution cannot be canceled out by any other summand, because if we add the power of a to the power of b, we get I, which describes our monomial. So this contribution cannot be canceled out, which shows that this polynomial is not the zero polynomial. And because its degree is smaller than p, this means it's non-zero for some substitution of a and b, which is what we wanted to show. So where does this reasoning fail in the multiplicity case? If we look at the polynomial x to the py minus y to the px, we do get that its coefficient to coefficient polynomial is not the zero polynomial for t to the p plus 1. However, it's a polynomial that's equal to 0 everywhere. And this means we get no line that attests to the fact that this polynomial is high degree. And now Roei will tell you more about how to analyze the plane case.
Thank you, Dan. So first thing I'd like to talk about is how to provide the right algebraic framework for the problem. So first we define evaluation tables. An evaluation table is a function from fp to dm to sigma ms. So these tables are exactly the inputs for the local characterization or testing problems. So we would like to identify those tables with algebraic objects. And we can do that by looking at the mapping from fpx to the set of tables. This mapping takes a polynomial and evaluates it and its derivatives on all of the fp to dm. And this mapping is not injective, but we can compute its kernel, which we denote by IMS. And then we get an isomorphism between tables and this quotient space, fpx modulo IMS. So let's talk a little bit about this kernel, how it looks like. So let's define gx to be x to the p minus x. Then the ideal of polynomials which vanish on fp to dm is exactly generated by gx1, gx2, and so on. So this is what's known as the combinatorial Nullstensatz, where you can see that one direction is trivial because every g to the xi vanishes on fp to the m. And this theorem says that the other inclusion is also true. And for the multiplicity case, we also have some kind of version of the combinatorial Nullstensatz, which says that IMS is exactly IM to the S. So it's generated by okay, so a basis for this quotient space. We choose a basis for the quotient space fp to the x modulo IMS by gx to the I times xk to the jk, where the weight of I is less than S and jk is less than p. And when I'm saying gx to the I mean gx1 to the I1 times gx2 to the I2 and so on. And you can actually see that all of these elements are reduced. And if you increase either the weight of I or one of the jk, then it becomes not reduced. So this is kind of an intuition why it is a basis. And using all we've done here, we can formulate an algebraic criteria for tables. So a table is a code word of our multiplicity codes, MRMP, if and only if the corresponding polynomial is of degree less than d. Now, given a table T, the way to prove the characterization part is we use our algebraic view of tables and represent it as the polynomials we've seen before. So it looks like alpha ij, gx to the I times x to the j, where the weight of I is less than s and j is of local degree less than p. And we would like to show that f has a I degree. Sorry, that if f has I degree, then there is some plane that proves it. The restriction to the plane is also I degree. So again, when we restrict to planes, we have to look modulo I to S, because the view of the algorithm only see the tables, not the polynomials. Now this framework is much more delicate than the Multiplicity 1 version, the Reed-Muller version. One reason is that the restricted polynomial is not reduced. So in the first case, the restricted polynomial was of local degree p, which exactly means it was reduced at most p, sorry. And now we need to compute its reduction first before start working on it. Also, it is not trivial to say that an element which is a coefficient of some I degree monomial exists and nothing else cancels it out, because the elements get mixed up in they just get mixed up, okay? And even after we find such a coefficient, we still need to say that there are some A1, A2, and C such that the coefficient is not zero. And exactly, it's not trivial like in the other case, where you had local degree less than P, and so you just got it for free. So the way to solve those problems are first, the fact that we chose a good basis. So this basis reduces nicely modulo I to S. What do I mean by that? I mean that if you look at the sum gx to the I times x to the j, then you just need to cut off the i's with the weight greater than 2, and you get the representation modulo I to S. Also, we choose a different weight function instead of the standard total degree. And this choice helps us to find such a coefficient, A of A1, A2, and C, which exists and also does not cancel out. It is not in the ideal I3M, A1, A2, C. So again, we use the ideal-based view to look for evaluation, which is non-zero. And yeah, so that's basically it for the characterization part. And now we'll talk a little bit about the robustness part. So let's say we have a function from fp to the m to sigma ms. And let's say that we are above the Rm testing dimension. And we know that for a lot of k-dimensional subspaces, the degree of f is less than d. When I'm saying the degree of f is less than d, I mean that f is a polynomial of degree less than d and its derivatives. So first, we just look at the values of f without the derivatives, and we get a function from fp to the m and fp. From the Reed-Muller case, we just get for free that this function is close to some p of degree d. Now, since pointwise f and p are closed, and since the k-dimensional subspaces form a uniform selection space, then we know that f restricted on H and p restricted on H will also be closed. And also we know that the degree of f is less than d on H, and this is for almost all H. And again, when I'm saying the degree is less than d, this is including multiplicities. So including multiplicities, we know that fh coincides with p on H. Now we start looking pointwise instead of on k-dimensional subspaces, and we say that for most points and for almost all subspaces through them, f on H will agree with p on H. Now we move from these subspaces to lines, and we say, let's look at all the possible results of chain rules for different lines through those points. So we just compute the derivative for every line through those points on this subspace. Okay, so we know that on those lines, we have an equality between the derivative of f restricted to a line and the derivative of p, which can be computed by the directional derivatives. This equality can be seen as a polynomial on A, which vanish for almost all A. And so again, since high degree polynomials, since multivariate polynomials cannot vanish on too many points, we know that this equality holds for all A. And so for all values, for all of those good values, fi on B and pi on B must be 0. And so in general, because we are given a promise that f is either close, far from a code or exactly in the code, we know that f must be exactly in the code. And that's it, thank you.